work, but it's not terrible, horrible work. And I can let Dan and Tibra, well, I believe they have a copy, and I'm happy to let you guys see this work through the arithmetic. But it is just arithmetic with gauge covariance derivatives, symmetries, and so on that get you to this point. So what is the point? The point is that the gauge variation of the abelian anomaly is the D of the non-abelian. So this is the relationship between, if you have an abelian anomaly in a gauge theory, suppose you have a gauge theory and you look at it, chiral transformations, the massless gauge theory, you look at its chiral transformations, you will in general get an abelian anomaly if you're in an even number of dimensions. The gauge variation of that anomaly is the D of the non-abelian anomaly in 2 fewer dimensions. Delta of omega 2n minus 1 is the D of omega 2n minus 2. And the exponent 0 means there's no dependence on a gauge parameter. The exponent 1 means there's a linear dependence on the gauge parameter, which is that. Yeah. This means what I said earlier, A comma F lambda to the n minus 2 is a shorthand way of writing A F lambda to the n minus 2 plus F lambda A F lambda to the n minus 3 and so on. Just shuffle them around. So it's fully symmetrized. The comma, if I did this, you would think it was a product. But it's not a product. It means you have to symmetrize over all that junk. It's D of the symmetrization of that thing. This is the symmetry. So, let me summarize what the main point of this rather semi-tedious mathematical exercise is, because this implies there is a connection between all the kinds of anomalies in gauge theories as you jump from even dimension to even dimension. They're all interconnected. And so a summary is that the abelian anomaly goes like trace of f to the n, which is D of omega 0 2n minus 1 of A, and that's because D of this trace is 0. So Poincaré's lemma tells us locally this is true. Delta D of omega 2n minus 1 on A is the D of omega 1 of 2n minus 2 of dA, where we can write this out, which is the D of the non-abelian. So the gauge variation of this form is the D of the non-abelian anomaly, and the abelian anomaly is the D of this form. This is called a Chern-Simons. Chern-Simons. So the gauge variation of the Chern-Simons form is locally the D of a non-abelian anomaly in one less dimension, or of one less form cell. Any questions up to this point? You're ready. So there's another viewpoint that I think I can sketch out in the remaining time. If you take the effective action of a gauge theory of massless fermions, then if there is an anomaly, the covariant divergence of this variation will not vanish. This is the current, and the covariant divergence of that will not vanish. So let's define operators that are this with that. In other words, it's G mu with the variation of A. So this thing acts on functionals of A, first taking the functional derivative of A and then taking the covariant divergence of the answer. You can show that these things obey a Lie algebra. So, an anomaly, they'll be the same as the group that, whatever the non-abelian group that A is or the gauge is from. So the anomaly is that equation. In fact, I don't want to waste valuable board space. So under this way of looking at it, an anomaly is basically XA, of course these depend on X, acting on gamma of A, is going to be something non-zero, so let's call it G. And it will be a functional of the gauge. So this isn't so far any big deal. It's just saying this covariant divergence isn't zero. Let's call it something, and let's call that something G. But now the commutators of these x's imply that XA commuted with GB of A is equal to F ABC GC of A delta of X minus Y, but that depends on X and that depends on Y. Because it's a functional variation at A of X, this will give